Good day. This is a PowerPoint set of notes. You should have the equivalent notes to copy onto. And we start with the Ka table. So coming down the left, it tells us about the strength of acids. It tells us how well they dissociate to produce H3O plus ions. So here is our Ka chart. And these six are at the same strength. This is very large. Essentially, they're close to infinity. Because you'll see arrows, it means the reaction goes to completion. And instead of writing H plus, or H3O plus, they've written H plus. You're going to get in the habit of writing down, say, HClO4 plus H2O becomes H3O plus ClO4 minus. But these six are strong acids. From hydronium down to water, we're now looking at weak acids. And they'll have Ka values. And down here, we're looking at some of the weakest acids, and you'll see an arrow pointing at them, so the forward reaction is not going to occur. And this is all how these chemicals react in water. How do they react with water? How well do they hydrolyze? And hydrolyze just means react with water. So if you see very large, that means they want to go to completion in water. So if we look at HCl, we're not going to find HCl, we're actually going to find H3O plus and Cl minus in solution. H2SO4, we're going to find H3O plus and HSO4 1 minus in solution. Now we're not likely to lose that second proton in water. Somewhere if we come down here, we see here's HSO4 minus. So HSO4 minus is a weak acid because it has a Ka value, and that means that not all the molecules will lose their hydrogen, lose their proton to become SO4 2 minus. So as we go down the chart, after we have our six strong acids that behave basically the same in water, then it goes down, 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 down because the Ka values get smaller and smaller. On this side, we're looking at bases, and the strongest bases are here. So we have two strong bases listed, and they will react with water and go to the left completely. These ones that are in the white background, these are all weak bases. And we would have to calculate something called a Kb. Ka is the equilibrium constant for these things acting as an acid in the forward direction. Kb is something we calculate from Ka. It's the equilibrium constant for these things reacting with water going the other way. So now we got to look at water. And when we have water molecules, a small fraction of them will react in such a way as to have a proton transferred to one water molecule to form hydronium, and the other water molecule that lost the proton becomes OH minus. So we end up with an equilibrium expression. This would be an overall expression for K equilibrium. But what we see is that's a liquid. So that means its density is going to be constant. So we can get rid of it. So we have Kw. And this is a very important formula to us. At 25 degrees, Kw is 1.00 times 10 minus 14. And that's for water acting as an acid, essentially. And this in turn turns out to be very important to us and allows us to do a lot of calculations, particularly at 25 degrees. But remember, we got rid of the H2O there because it's a liquid. And so this is an expression that becomes KWW for water. And it's put in a hockey rink because it's important. Like all equilibrium constants, it's affected by temperature. So if we're not at 25 degrees, we're going to have a different value for KQ. But most of your calculations will be based on being at 25 degrees Celsius. Well, for neutral water, then the concentration of H3O plus is going to be 1.00 times 10 to the minus 7. And same thing for the OH minus, 1.00 times the 7 big M. But what happens is if we add acid, the H3O plus will go up and the OH minus will go down. And if we add base, the OH minus goes up and the H3O plus will go down. So these things multiplied together have to equal 1.00 times 10 to the minus 14. That's what we're talking. One goes up, the other goes down. That's just the way it works. So we want to be able to find the H3O plus and OH minus for a 0.100 M solution of HCl. HCl is a strong acid and completely dissociates. So what that means is our H3O plus is going to equal 0.100. Well, if it equals 0.100, then the OH minus has to equal 1.00 times 10 to the minus 13, because it's 1 times 10 to the minus 1. And these two things multiplied together have to equal this amount. In other words, if we're trying to solve for the OH, we take Kw, divide by H3O plus, and it gives us the OH minus concentration. Now you might have heard about pH and pOH, and we like it. It's based on a logarithmic function, and that's because we can get these massive changes. There's a huge difference between something being 1 times 10 to the minus 1 and 1 times 10 to the minus 13. So it's a lot easier if we use the powers of 10 to describe the differences, and that's what logarithms are going to do for us. You might recall we used them on the earthquake scale. Well, they're used on pH. So, to go from H3O plus to pH, we punch in our concentration of H3O plus, we hit the log button. On my calculator it says log, and whatever I get, I hit the minus sign. So if I got a minus 4, I call it plus 4 for the pH. You just flip the sign. So you can try this out on your calculator. You can go 2.5 times 10 to the minus 9. Then you hit the log button, and then you change the sign. And when you do that, you get 8.60. And that makes sense. Our pH is above 7 because our H3O plus is below 1 times 10 to the minus 7. And we have to remember acidic pHs at 25 degrees are below 7. But if we are above 7, it means we're basic. And that's because we don't have even 1 times 10 to the minus 7 M of H3O plus. So that has to be automatic. Now I should talk about significant digits. And that's what it talks about right here. So what we have to understand is this times 10 to the minus 9 essentially translated to the 8 in this case, and that represents the power of 10. The trailing digits are the significant digits. So here we had 2 sig figs, here we have 2 sig figs, and this is a power of 10. Just like this has 2 sig figs, and there's our power of 10. That may take you a moment or so to get used to, but you don't want to lose marks for sig figs, so learn it quickly. Now, OH minus to POH, it works in the same way. The POH, the P really just simply means minus log. That's really all it is, a little p. So we go minus log of OH minus. So here we have a fairly big number in terms of base. We know it's bigger than 1 times 10 to the minus 7. So we go and punch this in, minus log it. And we get a pOH of 2.125. Now you might say, I wonder what the pH is. Well, it turns out we just have to take 14 and subtract this, and then we're going to get our 11.875 for our pH. And so that would be a basic pH. Now you're looking at sig figs, and you say, whoa, look at that. 3 sig figs, they're after decimal point. and there's our power of 10 in front. Now, reversing, going pH to H3O plus, we have to undo our steps in the right order. We already showed you how to go H3O plus to pH minus the log. So the first thing we have to do is we have to change the sign of the pH. So if I had a pH of 4, it'd become minus 4. And then I anti-log it, or anti-log it, or often that's inverse log on your calculator. So you have to have the right syntax, do things in the right order. And here's an example. So it says 4.25. So first thing is I'm going to make that minus 4.25, and then I'm going to minus or inverse log it. And what's belched out? 5.6 times 10 to the minus 5 big M. Now pH has no units, but our concentration of H3O plus has to have units. And it goes and talks about the sig figs again. We're getting there. POH to OH minus just works like the last slide with the pH going to H3O plus. So you change the sign and anti-log it. Let's do it for this example here. 10.234. We make it minus 10.234, and we anti-log it. We get 5.83 times 10 to the minus 11, and we have to put in the big M. And there's that crazy sig figs thing coming in again. So this is a chart you have to copy. It's like a road map. And in fact, I think we'll stop this video here and we'll carry on with it in the next video. So this would be a good place to stop.